Welcome to Study Loop.
Once again, welcome to a new problem. This time we have to deal with the center of mass. So we're given a problem and it involves the center of mass. Remember, if you uh, think about a geometric object like a rectangle, the center of mass in terms of the x and y coordinates will be at its geometric center. So this is the x coordinate, this is the y coordinate, this is the y center of mass, and this is the x center of mass. So that's kind of the idea behind the center of mass if you're dealing with regular shapes. But sometimes, though, in general, if you have a shape that's not regular, you could still get the center of mass. Or maybe if you have a solid object like a rod like that, you could still get the center of mass, but this time you're going to sum up the integrals. These are the formulas that are given for the center of mass, and y center of mass equals to 1 over m integral y dm. Remember, m is the total mass of the object. Okay, dm stands for the infinitesimal mass of the object. So you slice a small piece and then you call that dm. So that's kind of the information we're given. X and y are the coordinates of the object. So think about a thin rod like this. So we have a super, it's a super small thing, super small thing like this. So that's your y-axis. This is your x-axis. And then you have a super small thin rod. Maybe it should start at the origin, like right there. It's very thin. I'm just expanding it to make sure you could see it. The length happens to be L. And then the mass is M. And it has a cross-sectional area. So if you are looking at this side, like that, the cross-sectional area will be circular and it's going to be A. We want to find, this is part A, we want to find the, if the density rho is given by the total mass over the total volume of the object, the uniform object, we want to show that the x center of mass is at the geometric center. So another way of saying it is, if you do your computations right, the x center of mass and the geometric center will be coincident, and you can see if the length is L, then the geometric center has to be L over 2, and we're hypothesizing that that's also going to be the center of mass. So they want us to show that it's equivalent to L over 2. And then in part B, we're told that if the density of the object is proportional to the length, so think of an arbitrary object of length x. As you move along, this is x distance. We're saying that there's an alpha, which provides a constant of proportionality to x. So x, the density of this object, is related to the length of the object through a constant called alpha, where alpha is a positive constant, so alpha is greater than 0. So we want to get the x coordinate of the center of mass. So that's the information that we're given, and this is what we want. So we want to find, we want to prove that the center of mass is the same as the geometric center L/2, and also we want to find out the center of mass, the x-coordinate of the center of mass, if this relationship holds. We're going to start the problem in the next page, and we'll say that given that the density of the rod, rho, is usually mass over volume, and think about a circular rod like that. This is the length, this is the area, and so the volume is area times length. So we can change this formula to mass over AL. And that's the whole thing. But if it's infinitesimal, so you split or you slice it. If you slice it like this, you find out that mass is dm as opposed to the total mass, which is m. So the total mass is m, but then if you slice it, you get an infinitesimal mass. So at the infinitesimal level, if this relationship is true, you get to see that the mass becomes rho times AL. But at the infinitesimal level, we don't have L anymore. But this distance right here becomes dx. So instead of L, actually we should do it on the other side, so we don't confuse it with the mass itself. So on this side we should have said that the infinitesimal length, this infinitesimal length right here, that's the x, and then the infinitesimal mass is the m. The whole mass is capital M. So we want to see those relationships. Either it's the whole, which is the capital M, or capital L, and then the infinitesimal, which is the dm in terms of mass, or dx in terms of displacement or distance or length. So if this is true, if m equals to rho dl, you could see why it makes sense to say dm equals to rho a dl, but we're calling dl dx. So rho a dx. And the reason why we're using dx is because if you go back to the formulas that were given, we have x and y. So we want to be consistent in that instead of using L. So we'll just switch it to dx. So our dm becomes rho a dx, like that. But then rho is m over al. Then replace that and multiply that by a dx. These two cancel out, so we get m over l dx. Remember, our focus is on the infinitesimal dm. And the reason why we have to change this to dm, because we want to do some type of integration. If this is in terms of m and this is in terms of x, it's impossible to do a valid integration. So you want to have them everything with the same variable, so you can run the integration. So the center of mass in the x becomes, we're given this formula, 1 over m integral x dm. And then we start doing the replacements. We have 1 over m integral x dm is m over l dx. So m over l dx. It helps us to cancel out these two. We can pull out the l, and then now we have integral of x dx. Then 1 over l is a constant. We do the integration. So this is x squared over 2. But remember, if you can recall, our rod had a length of L. If if you go back, you see that this length was L. Okay, so then it means that we're starting from the origin up until a position X, or rather L. So going back means that you have to include those limits of integration. Okay, the limits of integration are from 0 up until L. So those are the same ones we're going to have right here. And then when we go back, remember these problems, you always have to think about the whole unit and the infinitesimal unit, and then you replace all your variables to be consistent as long as they have constants. So center of mass equals to 1 over L integral, or rather, we already did the integral, so we don't have to repeat that. This one is a constant, so it can stay outside. We have x squared over 2, 0 to L, x squared over 2, 0 to L. And this is decent because now if we plug in the L, we get L squared over 2, and then minus 0, because if you plug in 0 into x, you just get 0. So, we don't want that to happen. So this is 0 to x. And so we have 1 over L times L squared over 2. One of the L's cancel out. So then our center of mass becomes equal to L over 2, which is exactly the same as the geometric center. So the center of mass and geometric center are coincident. They happen to be coincident. And that's what they wanted us to prove. And that's just part A of the problem. That's the first part of the problem. This is part A. You wanted us to see if the center of mass and the geometric center are the same. We've done that. In the next page, we'll start in part B, where they want us to compute the center of not compute, but calculate the x coordinate of the center of mass, given that the density rho varies with x, like that. So that's the information we're given. But we're going to use some of the information we picked up from before, which is this one. dm is rho a dx. dm equals to rho a dx. But then you can see what rho is. Rho is alpha x. So alpha x a dx. Alpha and a happen to be constants. Okay, alpha and a happens to be constants. If the rod itself, if you think about the rod itself, and this piece is infinitesimal dm in terms of mass, if we want to get the entire mass m, we have to use integrals. So we'll say to get m, we have to do the integral of dm, and then it's the integral from 0 to L, because this point is the beginning and this is the end. Okay, so from 0 up until L. So m becomes, remember, we want to get x coordinate of the center of mass, but before we go to that, we have to compute m and change it to values which are easy and consistent to deal with. So this is integral from 0 to L. dm is alpha x a dx, like that, because that's what our dm is. And so we have alpha x a dx. Alpha and a are constant, so you can pull them out, 0x dx, and then do the integral. We have alpha a x dx. We have x squared over 2 from 0 to L. The constant is outside, so we can leave it out. If we plug in those numbers into the integral, we get L squared over 2. And that's a new relationship for the mass m. So m equals to alpha A L squared over 2. And you're thinking, why is that helpful? It is helpful because if you can recall, the center of mass is given by that relationship. And now we do have a value for m, which is alpha A L squared over 2 integral, okay, from 0 to L, then x dm. It's like you DM someone that's like, I don't know, Instagram or something. But the DM in physics is the infinitesimal DM. So alpha rho A dx. So dm is rho A dx. And that's what we're going to have here. Instead of this dm, we have x times rho A. We're going to have rho A dx. Okay, if you go back, you see rho A dx. This one is dm. So we're doing the appropriate replacements, and then we end up having, we flip it, so 2 alpha A L squared, okay, integral from 0 to L, rho A x dx. These two A's cancel out. This A and that A cancel out. The A's cancel out. And then we also had another x. So if this is rho A dx, this is rho A dx, dm becomes, we have to do more replacements. So going back right here, we see that we need to find the value, a different value of. There's a relationship between. Where is that? Right here. Rho is ax. Rho is ax. So we can say 2 over alpha L squared integral from 0 to L. Rho is alpha x, not ax. Alpha x times another x dx. So this rho, just to have it right there, was alpha x, linearly dependent. The alphas cancel out. So we have 2 over L squared, x squared, integral from 0 to L, dx. Now we can do the integral. I'm going to do that on the next page. So x center of mass becomes equal to, if we go back, 2 over L squared, which is a constant, and then we do the integral, x cubed over 3, and then this is from 0 to L. And so we have 2 over L squared, L cubed over 3. The 0 plugged in just gives you 0, so nothing else happens there. This L squared will cancel all the L's except 1. So our final answer for the center of mass, or the x, what we call the x coordinate of the center of mass in this case, given that relationship, becomes 2L over 3. Okay, 2L over 3. So, real quick, we get to see that we're given two formulas for the x and the y. For the most part, we're going to use the x. We want to find the x center of mass to see if it's same as the geometric center, and then we're given a relationship rho equals to alpha x, and we want to see what's the x coordinate of the center of mass. We use the relationships of rho, which is mass over volume. We change that in terms of area, and the purpose is to make sure that the dm has a specific relationship with the x and the area, and then we do the replacements. We end up having a replacement for the dm, which you can see is m over L dx. We plug that in right there. the m's cancel, you pull out the 1 over L, you do the integral, you end up getting the x center of mass being L over 2, which is the same as the geometric center, as you can see right there. And then finally, we need to find the x coordinate, given that alpha, or rho, is alpha over x. So this time we change things in terms of m, which is the total mass. And so we plug that into this formula for x center of mass to eliminate the m and write everything in terms of area and length, because that's what we're dealing with. We're dealing with the cross-sectional area and the length. And then we simplify that, we get the x center of mass being 2L over 3. Hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, bye.